Good evening. Welcome to the fifth live session of Fundamentals of Additive Manufacturing Technology. So today we'll be discussing on galvanometer and a numerical question, a photopolymerization based liquid aim, and a numerical question of the last week assignment question. So let's start with the session. So the first question is, what is the purpose of a flat field lens in a galvanometer and how does it help in beam correction? So a flat field lens in galvanometer, uh, first of all we'll understand what is the purpose of a flat field lens in a galvanometer. So the correct option is it helps in correcting the non-uniformities in the laser beam's intensity across the scanning field. Now, when a laser beam passes through a laser beam passes through a flat field lens in a galvanometer, um, it modifies the beam's profile. Why it does so? To ensure that the intensity remains uniform across the entire scanning area. To ensure that the intensity remains consistent across the entire scanning area. Now, this is important for applications where a uniform laser beam intensity is required for accurate and consistent processing, such as required for applications such as laser marking, engraving, or laser-based imaging. So, flat field lens in a galvanometer, it helps in correcting non-uniformities in the laser beam's intensity across the scanning field. The correction is essential because laser beams can often exhibit variations in intensity across their profile due to various factors such as characteristics of the laser source or the optics used to generate and manipulate the beam. Now, uh, uh, why this is not correct? Because amplifying the laser beam's intensity would require a different optical element like a laser amplifier. This would require laser amplifier, and it wouldn't directly relate to the purpose of a flat field lens. Scanning the laser beam across a wider area, this is typically achieved by the galvanometer mirrors, not by flat field lens. And creating a concave beam pattern, it is not a function of a flat field lens in a galvanometer system. Okay, so this was the reason for using a flat field lens in a galvanometer. Now, just I will mention that the correction is essential because laser beams can often exhibit variations in intensity across their profile due to various factors. So, moving to the next question. What is the purpose of working principle of digital light processing (DLP) projector in a perfectory system? Okay, first of all, we'll understand DLP projectors. These are based on micro mirror technology. Now, these projectors, they consist of array of tiny mirrors. Each of these mirrors corresponds to a pixel. On the projected image. Now these mirrors can tilt towards or away from the light source. Now in the context of 3D printing, the projected image is a pattern of light that corresponds to a single layer of the 3D object being printed. In 3D printing, the projected image is a pattern of light that corresponds to a single layer of the 3D object being printed. This is important. Now, uh, perfectory system, as we read here. Now, what happens in a perfectory system? Now, a vat of liquid resin this is exposed to a light projected by the discussed DLP projector. Okay. Now, the digital light mask displayed by the DLP projector creates a specific light pattern that corresponds to the cross-section of the 3D object's current layer. This pattern of light causes the resin to solidify or polymerize, forming the layer of the object. Now, the projector can quickly switch between different layers, allowing for the sequential creation of each layer of the 3D object. So according to these options, the working principle of the DLP projector in the perfectory system is it exposes the entire layer of resin simultaneously using a digital light mask. Now we'll understand why the other options are not accurate. Now the first one, it uses a laser to cure the resin layer by layer. This is a common technique in SLA. Common technique in SLA, stereolithography 3D printers, but it's not the working principle of a DLP projector. Now, heating the resin to initiate photopolymerization is not a typical approach in DLP based 3D printers like the perfecto system. Now, inkjet printed print heads to deposit liquid resin. It is a method used in some 3D printing used in polyjet printing. I'll just write one more line. Digital light mask displayed by the DLP projector creates a specific light pattern that corresponds to the cross section of the 3D printed object. Of the 3D printed object's current layer. Now this is the most important part. This pattern of light causes the resin to solidify or polymerize, forming the layer of the object. Subsequently, the DLP projector can switch between different layers allowing for the sequential creation of each layer of the 3D printed object. Okay, so these were the reasons behind the working principle of the digital light processing projector in the perfector system. So now the next question. The perfector system uses a flat field lens to maintain the focal point at a specific distance above the resin surface. Now, what is the purpose of this lens? Any answers? Okay. So, as we discussed, the perfector system. In the perfector system, the flat field lens serves the purpose of ensuring uniform curing of the resin across the entire build area. So the correct option is that to ensure uniform curing across the entire build area. Now, like we discussed, when using a DLP in a 3D printing system, like the light emitted from the projector needs to be focused onto the resin surface in a consistent manner to achieve uniform and accurate curing. A flat field lens is used to maintain a specific focal point at a set distance above the resin surface. This lens helps to distribute the projected light evenly, ensuring that the resin solidifies across the entire build area of the 3D printer. Now, what about the other options? The correct option is option B. Now, protecting the projector from raising spills. This is not the primary function of the flat field lens. This would typically be addressed through design considerations and protective measures rather than relying on a lens. And the flat field lens does not affect the printing speed or accuracy directly. It is primarily concerned with distributing light uniformly for consistent curing and filtered out harmful UV light. It is UV light protection. This is a consideration for the overall system design, but it is not a primary role of this particular lens in the context of uniform curing. Okay. Okay. So now the next question. Now we have a DLP projector with a resolution of 1920 into 1080 pixels. 1920 into 1080 pixels. Now the working area of the 3D printer is 200 into 100 millimeter square. Now it is asking to calculate the resolution of the machine at the maximum work area setting. So first we will find out the DLP resolution. DLP resolution is nothing, just calculate the total pixel. This will be 1920 into 1080. Let's calculate. This will be 2073606. Now the working area is 200 into 100. This will be 100 square. Now okay, yeah, we can start again. So now the print resolution is, this will be DLP resolution divided by the working area. This will be 273600 divided by 0. Okay, print resolution is working area by DLP resolution. This will be approximately 9.64 9.64506 into 10 to the power minus 3. Now since the pixel is square, so hence side of the pixel will be root over of 0.009645 will be approximately 0.09280. So the correct option is, okay, I have been mentioned the options. Okay, this is the answer. Fine. The next question now. So in a photopolymerization based liquid AM, what happens during the curing stage? Now, during the curing stage in a photopolymerization based liquid additive manufacturing, such as let's take example of SLA method or DLP method, the liquid resin solidifies by being exposed to light. Now we'll understand what happens exactly. This here we are talking about SLA or DLP. So in this photopolymerizer based 3D printing, a liquid resin is raw material is the liquid resin. Now, this resin contains special molecules, photoactive molecules that react when exposed to a specific wavelength of light. Let's say this light is a UV light. Now, when the liquid resin exposed to the appropriate light source, the photoactive molecules within the resin undergo a chemical reaction leading to cross-linking and polymerization. Okay, so this liquid resin contains molecules that react to specific, let's write it directly, let's react to UV light. Okay, now when these resin undergo chemical reaction, this leads to cross-linking and polymerization. Resin undergo chemical reaction leading to cross-linking and polymerization, and as a result the resin transitions from a liquid state to a solid state, forming the desired 3D object layer by layer. Liquid resin transitions from a liquid state to a solid state, forming the desired 3D printed object layer by layer. 3D object layer by layer. Now this exposure to light causes the resin to solidify and become bond and creating the structure of the printed object. The process is repeated for each layer until the entire object is complete. Okay. Now we'll talk about the other options which are not correct. The cooling down the model is typically not a part of the curing stage. Not a part of curing stage. Heating the liquid to a high temperature could potentially have a negative effect also on the curing process. Subjecting model to high pressure, this is not a standard procedure during the curing stage in the photopolymerization based 3D printing. The primary factor involved in curing is exposure to the appropriate light source. Now, the next question. The term undercuring in photopolymerization based liquid AM refers to what? Undercuring, does it mean insufficient exposure to light during printing, printing with a lower layer height, overheating the resin, or using a high power UV light source? Okay, so photopolymerization based liquid additive manufacturing undercuring refers to a situation where the printed object has not been exposed to sufficient light during the printing process. Now, we know it is not insufficient exposure to light during printing process. Now, we know that photopolymerization based 3D printing involves using light to solidify liquid resin and create layers of the object being printed. We already discussed this. Now, if the exposure to light is insufficient, if the exposure to light is insufficient, the resin may not fully polymerize. And cross-link. This will result in a partially cured or sometimes an uncured part. Now, this can lead to structural weakness, poor surface finish, and other defects in a printed object. Now, undercuring can be caused by factors such as inadequate light intensity, incorrect exposure settings, or insufficient exposure time for a given layer. It's important to ensure that the resin is exposed to appropriate light conditions to achieve proper curing and the desired mechanical properties in the final printed object. Now, printing with a lower layer height doesn't directly relate to the concept of undercuring. Layer height refers to the thickness of each individual layer in the 3D printed object. Now, overheating the resin would not be described as undercuring. Overheating might lead to other issues, not undercuring. And using a high power UV light source might actually help in achieving proper curing if the exposure parameters are appropriately adjusted. It wouldn't be a direct cause of undercuring. Okay, I'll just write the reasons of undercuring. Undercuring can be caused by factors such as inadequate light intensity, incorrect exposure settings, or insufficient exposure time for a given layer. These are some of the causes of the undercuring. Factors responsible for undercuring. Now the next question. Okay, which of the I think I missed the question. Just a second. Okay, it's fine. Okay, which of the following factors directly affects the curing depth in photopolymerization based liquid additive manufacture? So, curing depth before we start, we'll also curing depth is related to penetration. There is a formula which we'll also discuss. Curing depth is equal to penetration depth into ln of E max by EC, which is the exposure, maximum exposure by critical value of exposure. Okay, but this question is not related to those formulas. So it is here asked, which are the factors out of the following factors which affects the curing depth in photopolymerization based liquid air. Now, the curing depth, the correct option is light intensity and wavelength. Now, photopolymerization, as we know, it uses light to initiate the polymerization process in a liquid resin, causing it to solidify and 3D printed object. The light intensity refers to the amount of energy per unit area, while the wavelength refers to the specific color and or frequency of light used. Light intensity, amount of light energy per unit area, and wavelength, specific color or frequency of light used. Now, the depth to which a resin solidifies and cures depends on the intensity of the light and its wavelength. Higher light intensity can penetrate deeper into the resin, allowing for a greater curing depth, Additionally, the choice of wavelength is also important because different photo initiators within the resin are sensitive to specific wavelengths. So using the correct wavelength ensures effective activation of the photo initiators, uh, leading to proper curing. Using the correct wavelength ensures effective activation of the photo initiators, leading to proper curing. And light intensity, higher light intensity corresponds to a penetrate deeper into the resin, allowing for a greater deeper into the resin, allowing for a greater curing depth. Okay, so the layer, what happens with layer height? Layer height, it refers to thickness of each individual layer in the 3D printed object, and this affects the resolution and overall geometry of the printed part, but it doesn't influence the curing depth. Printing speed can affect the exposure time of each layer and the overall printing process, but it's not a primary factor that directly influences the curing depth. And resin viscosity, this can impact the flow and behavior of the resin during printer, but again, it doesn't determine the curing depth. Okay, so now the next question. Okay. The process of over-curing in a photopolymerization-based liquid AM can result in poor layer adhesion, reduced mechanical strength, warping of printed parts, increased curing speed. Now, the correct option is reduced mechanical strength. Now, overcuring occurs when the printed resin is exposed to too much light energy for an extended period. Overcuring. So, through these questions, we are understanding about undercuring, overcuring, and what are the factors affecting the curing depth, uh, and what happens during the curing stage. So, basically, we are trying to understand through about the curing process in photopolymerization-based liquid additive manufacturing process. Now, what happens in a process of overcuring? Now, in overcuring, printed resin is exposed to too much light energy for an extended period. Now, when resin is overcured, the polymer chains within the resin become excessively cross-linked and bonded. Well, some level of cross-linking is very much essential, for creating a solid and functional printed part. But excessive cross-linking can lead to, so this will lead to now polymer chains within the resin become excessively cross-linked and bonded. Now, what happens is excessive cross-linking can lead to brittleness and reduced flexibility, finally results in decrease in the mechanical strength of the printed object. Now, what happens during poor layer adhesion? Poor layer adhesion uh, is more likely to result from undercuring when insufficient light exposure causes incomplete bonding between layers. Now, warping of printed parts is generally associated with factors like uneven cooling, inadequate support structures, or improper printing settings rather than over curing. Increased curing speed would not directly lead to overcuring. Overcuring is about excessive energy exposure, not the speed at which curing occurs. Okay, so this was about overcuring. Now, the next question. Which type of photopolymer resin would be more suitable for applications that require high flexibility and impact resistance? The first option is standard resin with low elongation at break, rigid resin with high tensile strength, tough resin with a high elongation at break, brittle resin with low impact strength. Now, the correct option is tough resin with a high elongation at break. Now, for the this would be the most suitable choice uh, out of all the other options for high flexibility and impact resistance. Now, why? Now, elongation at break is a material's ability to stretch before it breaks. Elongation at break this is material's ability to stretch before it breaks. Now, resins with high elongation at break are more flexible and can undergo significant deformation without fracture. Okay. Now, in applications, now I'll just write resin with high elongation at break are more flexible and can undergo significant deformation without, I'll just write the short form, without fracturing. Now, in applications where impact resistance and flexibility are important, just let us say in some prototypes, products subjected to vibration, or parts that need to absorb shocks, a tough resin with high elongation at break would provide the desired properties. Now, tough resins are formulated to exhibit both high strength and high impact resistance. They are designed to withstand mechanical stresses and impacts without shattering or failing. The combination of toughness and high elongation makes the resin ideal for applications where flexibility and impact resistant are key requirements. Now, what happens when resins with low elongation at break? Now, this would not be sufficient suitable for applications requiring high flexibility uh, and impact resistance, as it would lack the necessary ability to deform without breaking. Lacks the ability to deform without breaking. Now, rigid resin with this is the correct option. Rigid resin with a high rigid resin with a high tensile strength. This would provide stiffness but not the flexibility and impact resistance needed for the specified application. And brittle resin with a low impact strength. This would not meet the requirement for a high flexibility and impact resistance, because brittle materials tend to break or shatter upon impact, making them unsuitable for applications where impact resistance is important. So these were the points regarding elongation and break for a tough resin with high elongation and break required for high flexibility and impact resistant, which are the type of photopolymer resin which would be required. Okay. Now the next question. Now the photopolymerization based liquid additive manufacturing is not recommended for producing parts that will be exposed to. Okay, I have mentioned the option: high temperature, UV light, mechanical stress, and chemical solvents. So the correct option is high temperature. So will photopolymerization resins used in liquid additive manufacturing process have a limited thermal stability. When exposed to high temperatures, these resins can, at high temperatures, these resins can soften, deform, or melt. Now this makes the parts produced through photopolymerization based process like SLA, DLP unsuitable for applications where they will experience elevated temperature. Now why not okay, we'll understand why. What about the other options? UV light, mechanical stress, and chemical solvents. So photopolymer parts are typically cured by exposure to UV light during the printing process. So exposure to UV light is not a concern after curing. Now mechanical stress, while some photopolymer parts may have limitations in terms of mechanical properties, they can be designed and selected for applications involving mechanical stress to a certain extent. Next is these can be susceptible to certain chemical solvents that can degrade or dissolve the resin depending on the specific type of resin used. However, this is separate from the concern exposure to high temperatures. Okay, so now we will solve the numerical question. So this is the lengthy question which you must have come across in assignment 4. Any queries or doubts? So this is a SLA system where we have been given a particular resin which is used in a vat of size. This is meter cube. And these are the specific stations of the system. A laser beam with Gaussian intensity distribution is used to cure the resin. The laser beam reduces its intensity by 1 by E square, this is square, at a distance of 100 micrometer from the center of the laser beam. It is desirable to have a maximum curing depth D subscript to be 2 times the penetration depth. The spacing between two single beads is 2 into laser beam radius. This is the graph of curing depth and exposure which is given, and we have to determine the following things. So first I will write what is given in the question. The size of the vat is 0.45 into 0.45 into 50. Now consider this is the beam. The beam radius is given. It is given that the curing depth is 2 into penetration depth, that is 2 times of laser beam radius. Now vat means the container. Okay, so this is the graph of curing depth, and curing depth is in mils, which is like 1 mil as it is written, 0.0254 millimeter. Okay. Sorry for the break. Okay. So now we'll solve the question. We'll write out what is given. So CD is the curing depth, DP is the penetration depth, E max is the maximum exposure, and EC is equal to critical value of the exposure, which we don't have, we have to find out. Okay, and the formula between the curing depth and the penetration depth is, this is a very important formula. CD is equal to DP ln E max by EC. Max by EC. Now from this formula, since this is a ln, so CD is equal to DP. This is the first option which are solving now. Okay, we have to find out the value of penetration depth in mils. So CD is equal to DP ln, we will write ln E max by EC becomes ln E max minus ln EC. Now the curing depth we have. Now from this graph, as you see, I'll take this point, okay, the point in 40, and corresponding to this, okay, this will be, if we find out the number of divisions, 2, between 2 to 4 we can 1, 2, 3, 4. So consider this 2.4, 2.8, 3.2, 3.6. So we can assume this is 3.8. Okay, and this we are taking it as 40. Approximately 40 we are assuming this. 3.8 and 40. So I am taking it as 3.8 and 40. 40 is in exposure is in 40 mJ per centimeter square, that is in mils. So I'll write the equation. 3.8 is equal to dP ln 40, which we got from the graph, and 3.8 also we got from here, minus ln EC. This becomes our equation 1. Now this is at 40. Okay. Now again we will find out at 60. Again we'll draw the vertical line at 60, and if we draw horizontal line, so this will be approximately, if we consider this as 4, 4.4, 4.8, so 4.8 I am taking, and this is 60. So I am taking 4.8 is equal to dP ln 60 minus ln EC. This is equation 2. Now we'll simplify and write this equation now. This will be ln EC is equal to ln 60 minus 4.8 by dP. This will become now we will put this ln EC value here in now upon solving both these equations we will get solve equation 1 and 2. You will get 3.8 by dP is equal to ln 40 minus ln EC, or ln EC is equal to ln 40 minus 3.8 by dP. This I am continuing from here. Okay, this already we got. Now this is, we can write equation 3. Now we substitute equation 3 in equation 2 and we get so this here we've got one equation ln EC here, so we are substituting the both values. So ln 60 minus 4.8 by dP is equal to ln 40 minus 3.8 by dP. This will become ln 60 minus ln 40 is equal to 4.8 by dP minus 3.8 by dP. 3.8, this is 4.8. Now this will become ln 60 minus ln 40. Let me calculate. This will become 0.44, approximately 0.405465 is equal to 1 by dP 1 minus 4.8 by 3.8. Now solving this will become dP is equal to 2.466, or we can approximate it to 2.5 mil. Answer. So this is your first answer. This is the penetration depth. Okay. So we will also need this value further. So we will mark it. Okay. again we'll continue with solving our next question we have been asked. To determine the value of critical exposure in mj per centimeter square. Okay, this is megajoule per centimeter square. Second question. Critical exposure EC in mj per centimeter square. So I'll just again recap that we have been given a reason of the container size having the volume, and we have been given a laser beam of, this is the power of the laser beam. This will also be required further, and the laser beam reduces its intensity by 1 by e square at a distance of 100 micrometer from the center of the laser beam. And these are the condition. It is desirable to have maximum cure depth to be 2 times of the penetration depth. dp is CD is 2 times of 2 of dp, and the spacing between two single beads is 2 into laser beam radius. So we are finding out the penetration depth which you already got, and next is we will find out now the value of critical exposure. Now the critical value exposure, we here we did not find out EC. Okay, we only found out the DP. EC got we substituted the value of EC from one equation to another. So now we will take one condition. Let's take 4.8, this equation. 4.8 is equal to DP ln 60 minus EC. Where I got this equation? I found out here itself. This part. Okay. At 60. I am considering the point at 60. 60 is what? 60 is your exposure. So at 60, this equation we have already written further, so I am not repeating. CD is equal to dP ln Emax minus ln EC. Okay, so here 4.8, now penetration depth we got here 2.5, so we will substitute the value here, 2.5 ln 60 minus ln EC. From here you will get 4.8 by 2.5 is equal to ln 60 minus ln EC. So here ln EC is equal to ln 60 minus 4.8 by 2.5. This becomes ln 60 minus approximately 1.92, and EC is equal to E of 2 will become 17. So this, if we find out, it will become 8.75 mj per centimeter. This is your second answer. Okay, so now we covered this and found out this. Now we have to find out the maximum curing width of a single bead in micrometer. So how to find out this? Maximum curing width of a single bead in micrometer. Now the formula for single bead curing width is now 3. Okay, so it is curing width is, this is maximum curing width, is, this can be found out through maximum energy. Okay, so CW is equal to W naught to CD by dP. Now this is the R value where beam intensity, as it is given here, this is the R value. Intensity, beam reduces its intensity at a distance of 100 micrometer from the center of the laser beam. Okay, so this is the R value where beam intensity reduces. I hope you are clear. Reduces intensity by 1 by E square. Reduces intensity by 1 by E square. Now we are given that CD is equal to 2 of dP. Here we have been given desirable to a maximum curing depth to be 2 times the penetration depth. So now CW is equal to W0 by 2 of dP by dP. This gets cancelled. So we have, sorry, I missed a 2 here, 2 into dP. So this gets cancelled here. So this will be 2 W naught. This will be 2 into 100, which is given. W naught is equal to 100 given 200 micrometer. So this is the third answer. So we now found out the maximum curing width of a single bead in micrometer. Maximum curing width. Next question. Next is we have to find out the scanning velocity in meter per second. So the formula for the scanning velocity you will get in the lecture videos. I'll write out here. Scanning velocity dx is equal to root over of 2 by pi P naught by W naught 1 by EC exposure exponential of minus CD by dP. Now this is given in our question 500 megawatt. Okay, so we will put all the values here. 2 by pi into 500 into 10 to the power, we'll convert into terms of watt everything, into 10 to the power minus I think this is in, okay, it is in milliwatt, not megawatt, sorry. This is in milliwatt and 100, this is in micrometer, so we are writing it into 10 to the power minus 6, 100 into 10 to the power minus 6. Now into, this will be 1 by EC. EC is just we found out 8.75 here. 8.75. This is megajoule per centimeter square. So we will convert it into joule per meter square. So when converting, this will become 1 into 10 to the power minus 4 by 8.75 into 10 to the power minus 3. Now this will exponential of CD we found out we know the relation 2 dp by dp, so this will get cancelled. Now this will become 2 by pi into 5 into 10 to the power 3, this all will get cancelled. This will become 10 to the power 3 into 1 by this will be 8.75 into point of minus 2. This will be 0.75 into 5000 into this will become 0.114 into 0.135. Now this will be approximately 6.094 meter per second. Now I have a thing to mention. See, here I took the points 40, 60 and approximately correspondingly I took the your depth. Now someone may select 20, someone may select 80, it depends. So that is why this question we will like in GATE exams we have a range. Between that range the answer should come. So this will also be like that, because once you find out the EC DP and EC, your question accordingly subsequent questions will also matter according to that, because here we substitute the value which we found out, the EC value we put it. So whatever EC we get, the accordingly the scanning velocity will vary with accordingly that. Next is we'll find the time for scanning the entire area of the vat. We'll just highlight this answer which we received. This is the fourth answer which we solved. Okay. So next again we'll find out now again we'll find out the time for scanning the entire area of the vat. For this we have again one more formula which you must have come across in the lecture videos. Time for scanning the entire area of the vat T. That means, okay, suppose let's consider this is as a x-axis and this as y, and this let's consider these are some of the strands, okay, and let's consider this as the distance between each strand, or this will be known as spacing. S is the spacing. Now this length is, we know, 0.5, 0.45. How it is known? Because here it is given 0.45 into this is length into width into height. Okay, so here we know the length. L into W into H given, which is 0.45 into 0.45 into 0.45 meter cube. Now the time for finding this for scanning is, formula is T is equal to A by K root over of pi by 2 EC, which is exposure, and T0, this is the power, CD curing depth, penetration depth. So we have a new, A is the area, we have a term K. Now K is related to spacing. Which I was mentioning here. Okay, now we know that spacing is equal to, or S is equal to K into W naught, and area is equal to 0.45 into 0.45 meter square. Now K is equal to spacing by W naught, or S is equal to 2 into W. Now in our point 3 here we have been given that the spacing between two single beams is 2 into laser beam radius. Okay, so according to this, K is equal to 2. That is why I wrote here from point 3 of question. Now we'll substitute the values in this formula. Now T is equal to area, which we got 0.45 into 0.45, by K is 2 root over of pi by 2. EC is 8.75, which we got earlier. It is since it was millijoule, so I have converted it into -3. Now by P naught we are given the question 500. Here we have been given here 500 milliwatt. So again we write here 500 into 10 to the power -3. Okay, exponential of 2 dp by dt. With this relation we are already used it earlier. So solving this we will get 0.10125. This will become 1.25 into, this becomes 175 into, this becomes exponential of 2 becomes 7.38. Now on solving this, approximately we will get 163.65 seconds. So this is the answer 5. Okay. Now the next question, the last question, this is a little bit lengthy. Ratio of exposure in hills and valleys, EH by EV. Okay, H and V are subscripts. Now we'll solve this. Six is ratio of exposure in hills and valleys. Now EH by EV. Now we have different for peaks for hills and valley formula. Different formula of exposure for peaks of hills and valleys. Now so for peaks we have NS is equal to number of spacing is equal to plus minus 2.146. This is, you will get this from the videos, from the graphs. This you have to refer lecture videos. Okay. Now spacing is equal to kW naught. This we already know. Now k is equal to 2, which is already given. Okay. Now here we know n is equal to plus minus 2.14 by 2. Okay. I'm sorry, I just wrote this different. This is ns. Okay. So this becomes plus minus 1.07. Now we will consider this as minus 1, 0, plus 1, because here it is given that less than 2. Where it is given? It is given here in our question that so here it is given the spacing between two single beads is 2 into laser beam radius. That is why we are not considering above that. Plus minus, this minus 1, 0, 1. Now okay. Now we have to, what is we have to do here is we have to find out EH by Emax, that is for hills ones, and for valleys ones EV by Emax. Now we know EY0, that is the exposure, is equal to Emax exponential of minus 2y square by W naught square. Now this y here becomes ES0 according to a spacing between a single strand. So we will consider that this is S, y is equal to S by W naught square. Now EH, now we'll write the formula of hill. So Emax, EH is equal to Emax exponent of 2, S is equal to 2 whole square plus Emax 0 plus Emax of minus 2 into 2 whole square. We expanded this. Okay. Okay, this is for minus 1, 0, 1. So accordingly we are doing. Now EH is equal to Emax of exponent of, we'll solve this, minus 8 plus exponent of 0 plus exponent of minus 8. Now EH by Emax will become 2 exponent of minus 8 plus exponent of 0 plus 1. Finally this will become EH by Emax is equal to 1.006. This is your equation 1. Similarly for valleys we will find out good to go. So for valleys, similarly, n is equal to, the formula is plus minus 2.146 by k minus 1 by 2. Now k is equal to 2, which is given. So n is equal to plus minus 2.146 by 2 minus 0.5. Now upon solving this, we get 0.573. So here n is equal to minus 10. Now EV, exposure of valleys, is equal to, formula is E max S by 2 minus S 0 plus E S by 2 0. Now this you have to refer from graphs. For valleys I am considering according to graph we have to take. There is a graph which is, we will refer from the lecture videos, difficult to draw here. So now EY0 is equal to E max exponent of minus 2y square by W naught square. Now this becomes E minus S by 2 comma 0 plus E S by 2 comma 0. Now E max exponent of minus 2 by 2 whole square plus exponent of minus 2 into 2 by 2 whole square Now from here we have EV by E max is equal to 2 of exponent of minus 2. This becomes 0.270. This becomes your equation 2. Okay, so from equation 1 and 2 we have EH by EV is equal to 1.006 by 0.270. It comes 3.72. This is your final answer of ratio of exposure of hills and valleys. Okay, so this was the question of SLS system of last week assignment. This is a lengthy question, and again your answers will vary according to the points which you have taken for exposure and pure depth. And that is why for these questions we have a range between which the answer should lie, as in like your gate question. Okay, so any doubts? Okay, so if there are no further doubts, we'll end the session. Thank you for attending the session. Let's meet again next week. Yeah, any doubts? Okay, I'll explain you. Yeah, sure. So, okay, so we have been given a reason, okay, and which is used in a container of uh, this this is the dimension. Okay, now we have been given a laser beam, okay, which has an intensity distribution used Gaussian intensity distribution used to cure the resin. Now this laser beam reduces its intensity by 1 by e square, distance of 100 micrometers from the center of the laser beam. So this is the vat of container, and the laser beam, uh, this considers the laser beam, and it is given that the spacing between, this is a bead and this is another bead, the spacing between two single beads is 2 into laser beam radius. And the one more condition is given, that it is desirable to have the maximum curing depth CD is equal to 2 times of penetration depth. Now we have to find out all these values. So this is your working curve. Now in this working curve we have the exposure in x-axis and this curing depth in y-axis. Now I have considered 2 points here. One is in exposure at 40 and one is at exposure at 60. And correspondingly for that I found out the cure depth 3.8 for 4.8. Okay, just remember this. Now this is their formulas. CD is equal to penetration depth in the ln of E max by EC. E max is the maximum exposure and EC is the critical value of exposure. So from in question 1 you have to find out the value of penetration depth. With this formula you find out at 40 and 60, put the curing depth, penetration depth, and by solving the two equations you will get your penetration depth. Okay, so this penetration depth is 2.5 for me when I have taken the value of exposure at 40 and 60. But again, if you take different exposure, your penetration depth may vary, but it will form certain range is given. So it should come under within that range. It will come under within here. Even if you suppose you take a penetration depth, you take a EC of 60, 80, 60 and 80. Accordingly, your answers will vary. So next, we have to find out the critical exposure. So we have already got the penetration depth GP. So we are again finding out with this formula. We have already got this equation. We are finding out with this by putting the value of penetration depth as 2.5. We are solving the equation and getting the critical exposure as 8.75 joule miljoule per centimeter square. Next is we have to find out the maximum curing depth of a single bead. Now how to find out the maximum curing depth of a single bead? The maximum curing width is, your formula is W naught 2 CD by DP. Now you have been given a condition here that your curing depth is desirable to have curing depth. CD is equal to 2 times of penetration depth. So you're using that condition and solving, then you are getting as your answer is 200 micrometer. Now W is given 100, as your W naught is given 100. 100 is your distance of 100 micrometer from the center of laser beam, reduces its intensity at distance of 100 micrometer from the center of laser beam. So with this you got the maximum curing width. Now next is the scanning velocity. The scanning velocity, you have been given the formula, so you just have to find out the values. EC you already found out earlier. CD and DP, CD is 2 times of DP. You will use the condition. This power is given in your question, 500 mega milliwatt, and similarly you put all the values and solve for scanning velocity. So here you have to be mindful of these conditions which have been given. CD is equal to 2 of DP, and this again varies depending on the values you got earlier. EC, which you have already found out here. EC is your critical exposure. We found out the critical exposure here. Next is your time for scanning the entire area of the vat. So consider, so these are, let's consider this an X and Y axis. These are various strands. So we know that between two strands, the space between is known as spacing. Now spacing, this is your volume of the beam is given. It is L into W 0.5, which you have been given here. 0.5 into volume of the container, you know, 0.45 into 0.45 into 50. So length is, that is why you know the length, which is length of a single strand is 0.45. So from there you get the area also 0.45 into 0.45 meter square. So you know the formula of the time for scanning the entire area of the vat. So accordingly you put your EC, critical exposure, CD is equal to 2 into dP, P naught, which is 500 milliwatt, and the area 0.45 into 0.45 K. Now what is important is K. How to find out K? Now K is related to spacing. So spacing, which we know from the lectures, that is equal to K into W naught. So S, we have noted the term S for spacing. S is equal to 2 into W. From where we get 2, K is equal to 2. It is given here that in the spacing between two single beads is 2 into laser beam radius. So from there we understand the spacing is 2 into W naught. So with this we get the relation S is equal to 2 into W. So here we substitute all the values and get the time required for scanning the entire area of the vat. Next is we have to find out the exposure time ratio of exposure in hills and valleys. Okay, so there is a particular graph in your lecture videos. So suppose this is the hills and valleys. So you need to find out the exposure between the ratio of exposure in your hills and valleys. So for peaks we have this particular relation, and for valleys we have this particular relation. Okay, so accordingly we solve this for maximum exposure, uh, Emax by EH by Emax. We solve first for EH by Emax, that is exposure of hills to maximum exposure. Then we solve for exposure of valleys to maximum exposure, and subsequently we get the relation EH by EV, that is exposure of hills to exposure of valleys. Now how do we solve that? We take this relation from our lecture videos, that is for hills this is the relation, and for the valleys this is the relation. You put, main is you put the K is to spacing, K is equal to 2 W naught, is the relation which we are using, and you solve with this equation. You consider now what we have to do is, here first we took the relation, you found out S is equal to K W naught, and you found out this N, the value. This is in plus minus. So here we got plus minus 1.07. So we are assuming it is minus 1 0 plus 1. Okay, so with this N value we are solving for the exposure of hills. Similarly, we are doing this for exposure of valleys, and thus we are finding out. Okay, so is it clear? So main is you have to consider, yeah.
Question number 13.
Sorry?
Question number 13.
Okay, I want question number 13. So is your assignment due date over? Yeah, I'll stop the recording. I'll start again. Okay, so this is the Gaussian intensity distribution at the beam center. So this is the most fundamental mode, fundamental TEM mode is TEM 00. Now among all the given options, the next basic mode is, so for this we have to also understand what is TEM. The next basic mode is TEM 10. Now it has one nodal plane. This is, see, earlier this had 0 nodal planes. Why this we are considering is, this has one nodal plane in both x and y direction. And TEM10, I don't remember like which. This is the Gaussian intensity distribution, and TEM11 we know it is a like a donut like intensity distribution, the dark center and bright ring around like it. But here I think this is a ring like distribution, TEM10. So here in this question, as we see, the distribution is, I am not getting the exactly TEM10 distribution number, the name. Just 1 second, I'll check it. Tem's are usually like this. Yeah.
uh, depth of penetration given the
Hmm.
working of the
Yes.
photo. So I using the working curve, I got an answer
Mm-hmm.
for depth of penetration as 5.87 mils.
5.87. Okay. So
Yeah,
what? Uh-huh.
and I got that answer correct
Mm-hmm.
because range given was 4.5 to 6.5 for
Okay.
correct answer.
Hmm.
So I my calculated value was 5.87.
Hmm.
So I got that correct.
Okay.
But then the next value, once we get DP,
Critical exposure.
yeah, critical exposure. That I get 7.77
Hmm.
millijoule per centimeter square.
Okay.
So that answer I get wrong as per the
As
quiz
per your ray is okay.
because that falls outside the range. The range
Okay.
given there for
Yeah,
correct
yeah,
answer
yeah,
6
yeah.
to 7. Mine was 7.77. So they marked it wrong.
Okay.
So that's fine if it is one answer. But then what happens? This EC value we
Yeah.
use
It is
oscillate,
like we are
oscillate
linked. Okay. Yeah, I understood.
time. So all the answers have gone wrong. Gone wrong because just is falling just a bit outside the range, acceptable range. So I think that range is too tight.
Okay, what you can do is just mention this in the announcement tab. Okay, so we'll
Okay.
look into it because the people who are correcting this are different. Okay,
Yes.
so and they have provided this range. So please
Yes.
mention this in that announcement tab. I think your questions will be answered.
Okay.
Surely.
Okay.
Since
Fine.
your penetration depth has been clear, but still your other values like EC and scanning velocity, rest all will be changed.
Yes.
Your, I
Yes.
think you must not be getting your scanning velocity time. Everything will be different.
Yes,
Yeah,
scanning velocity also I'm getting very, I mean, my answer is 6.9.
yeah,
And what they are expecting, they marked it wrong.
yeah.
You're saying they are taking it only up to like 6.
So I will suggest you to just write in the answer announcement tab. I'm
Okay.
sure someone will answer
Yes,
your query.
I'll do that.
Yeah.
Thank you.
Okay.
Yeah.
Okay. Okay then. If are there any other doubts? Okay, so we'll end the session. Thank you all for attending. Thank you.